Welcome back. This is EC253C and this will be lecture 10. So far we have discussed about microprocessors, particularly 8085 microprocessor. Then in last lecture we moved to microcontrollers. I introduced what microcontrollers are, how they are different from microprocessors, and we discussed very briefly one of the microcontrollers, 8051. I also told you that there are hundreds if not thousands of microcontrollers available in the market. I named a few. So today the first thing we'll be going to discuss is about how to choose a microcontroller. When we have to use a microcontroller in a particular application, we are designing a system and we need a microcontroller to control it. For example, maybe we are designing an AC, or maybe a washing machine, or some other thing, some other product where we need automation, where we need microcontroller to control its output, to control its functioning. The first question that arises, which microcontroller to choose? How to choose a particular microcontroller? Why I can use one microcontroller and why I can't use another microcontroller in a specific application? So what are the criteria for choosing a microcontroller? How do I choose? How do I proceed? So choosing a microcontroller. Criteria for choosing a microcontroller. Because each microcontroller is unique. Some have different instruction sets. Each has a different instruction sets, unique instruction sets, unique hardware, and also unique functions. So basically, whenever we have to choose a microcontroller, there are three criteria in choosing a microcontroller for a particular application. Number one, that is that the selected microcontroller must meet task or computational task with the task at hand efficiently and cost effectively. What does it mean? We have to do computing, we have to use microcontroller for that. So different microcontrollers have different computing capabilities. So first thing, before selecting a microcontroller, we should know that this particular microcontroller will be meeting my task, my computing tasks, my whatever computing I have to do in my system, in the system I am designing. This particular microcontroller I am choosing, it will be able to deliver that task efficiently and also cost effectively. So there may be three microcontrollers which can do my job efficiently, but out of these three, one may be very cheap and others may be less cheaper. So basically, to do the job cost effectively, I will choose the cheapest one. But at the same time, that very microcontroller should do the task efficiently. So the first criterion for choosing a microcontroller is that whatever task we have at our hands, whatever the computing task we have at our hands, the selected microcontroller should be able to deliver that task, should be able to deliver that computing task efficiently and also cost effectively. And how do we judge whether a particular microcontroller will be able to deliver that task or not? There are many things. For example, we check for speed. In different applications, we need our microcontrollers to run fast or maybe faster in some applications. So speed is one of the criteria. How fast is the microcontroller, or what is the highest speed that the microcontroller supports? As you may have seen, when you purchase a laptop, you see the processing speed, sometimes something like 1.6 gigahertz, 1.8 gigahertz. Same is with microcontrollers. They run at lower speeds like megahertz. They run at megahertz speed like 16 megahertz, 20 megahertz, 40 megahertz. But we have to see, before using a microcontroller, we have to see what's the maximum or highest speed that this microcontroller supports, and does this highest speed fulfill my needs or not. These things, this speed and other information about a microcontroller, we may always get from the specification sheets that are issued by the company that has manufactured these microcontrollers. So the first thing that we have to see is whether the microcontroller I have chosen meets the tasks at hand efficiently and cost effectively. And how we do that? First thing we check is its highest speed. We also check its packaging. In what package it comes. Last time I have discussed what do I mean by packaging. Packaging mean whether it comes in dual inline package, whether in quad flat package, do we have an SMD package for it, and other things. This is very important because in some applications DIP package is something like this. We have a rectangle like IC and we may have pins on both sides. On the other hand, quad flat package is something like this. In some applications, due to space constraints, we may be using quad flat package. For example, if we are designing a smartwatch, usually quad flat package is more suited, because smartwatch is in the shape of maybe a rectangle or a circle. So this package is more suitable instead of this. So we have to check what are the packages that the company manufacturing this microcontroller delivers. Does this microcontroller come only in DIP package, and which package do I need in my particular application? This is the second thing. In the first criteria, we also check for power consumption. And this is especially critical for the products which are actually battery powered, which are installed in remote areas where we can't plug in the system into the mains every time. So we have to see what's the power consumption. We have to choose a microcontroller which consumes less power. We may also check for the amount of RAM and ROM, because ROM will be used to store our program. We have to see the program we are going to write for this particular application, the number of instructions. Will those instructions, is the ROM of the microcontroller sufficient enough to hold those instructions? The data we are going to use, is the RAM enough? These things. Is the memory enough for our program, for our application? We will also be checking the peripherals. What do I mean by peripherals? By peripherals, we mean that what are the extra features that this microcontroller gives me. Is there an inbuilt ADC, analog to digital converter? Because in most applications I will be needing an ADC. So if there is not an ADC, an inbuilt ADC present in microcontroller, I may have to attach it externally, and that will add to the complexity of the circuit. So if I have to use ADC, I will check whether this particular microcontroller has an inbuilt ADC or not. So I will always prefer in some cases where I need ADCs, because in most of the cases the data is coming from the analog world, like the pressure readings, like the temperature readings we get. They are all analog in nature. So if we need an ADC, we'll always choose a microcontroller which has got an inbuilt ADC. There are maybe other peripherals also. Also, we have to check the number of input output pins, because that is important, in the sense that greater the number of input output pins, greater is the number of input output devices I will be able to attach to my microcontroller. For example, if a microcontroller has 3 IO pins, I will only be attaching 3 input output devices, maybe a button and 2 LEDs. But if I need more sensors to be attached to my microcontroller and more actuators, maybe motors, maybe an LCD to my microcontroller, for the complete functioning of the system, I need a microcontroller with sufficient number of input output pins. Same is the case with timers. We have not discussed exactly the function of timers, but when we will discuss, you will come to know what's the function of timers. And it is also an important consideration, because sometimes we need more than one timer in a particular application, so we have to choose a microcontroller with more than one timer, or in some application we may need 3 to 4 timers, so we have to choose those microcontrollers with 3 to 4 timers in it. Another thing we are looking for is how easily we can upgrade to higher performance versions. If there is a new version of this microcontroller in the market of an year, can I upgrade easily? So that's an important thing, because if there is a new version, it should be very easy for me to upgrade to the new version. It should not be like I have to write the new code, I have to do everything from the scratch, because then a lot of time will be wasted. If 6 months down the line I have a new version, the company introduced a new version of this microcontroller, it should be very easy to upgrade to that microcontroller. And there is one more thing, that is price. It's very critical. Actually, the price means cost per unit. What's the cost per unit of the microcontroller? I'm getting all these things maybe in a couple of microcontrollers, in 2 microcontrollers. Of course I will choose one with less cost per unit, because this is important in terms of the final cost of the product in which this microcontroller will be used, because at the end of the day I have to sell the product. So this was the first criteria of choosing a microcontroller, that we have to meet the task at hand efficiently and cost effectively, and that includes we may be checking speed, the maximum speed it supports, packaging, power consumption, amount of RAM and ROM it has, what are the peripherals and what peripherals do I need, number of input output pins, timers, number of timers, in fact also number of interrupts, timers and in number of interrupts, how many interrupts I need, and does this particular microcontroller have those number of interrupts, and also then the cost per unit of this microcontroller. The second criteria we usually check is the ease of development. The first criterion is done. We have selected a microcontroller that's meeting the computing task at hand very efficiently and also cost effectively. Okay, now I also have to check how easy it will be to develop a product around this microcontroller, and it includes the key considerations here are the compilers available which will be used when I write a program in high language to change it into assembly language program. Are the compilers available? Are there emulators wherein I can emulate the functioning on a system only before burning the program physically into a microcontroller? And what is the technical support? If I get in a problem, can I search the internet and get the results? How much technical support is available? How many discussion forums are available online? So this is very important, because this helps us in development. If there are a number of compilers available, there are emulators available, there's a lot of technical support available online, the development around this microcontroller will be easy. So we check how easy it is to develop a product around this microcontroller. The third thing we check is the availability. This is a very important criterion in choosing a microcontroller. Is the microcontroller available, and how readily it is available? How easily can I get it? Where from I am working? Can I get it in here quickly? And this also includes whether the needed quantities are available and whether the needed quantities will be available in future. This is a very important criterion, because if in future this microcontroller is not available, then I have to redesign my product around a different microcontroller, and that will waste a lot of time. So before using a microcontroller, I have to check what is the availability in the market and what will be the future availability. One of the key considerations here is that I check whether this microcontroller, there is only one manufacturer or there is more than one manufacturer available in the market, and how big is that manufacturer, because it's less common that a big company will stop working. So if there are more than one manufacturers of a particular particular product, particular microcontroller, I will obviously select that microcontroller. So availability in the market, both now and in the future, is very important. Usually companies like Microchip and NXP, we use their products, Microchip and NSP, because their products are stable and these companies are mature, and also they have a lot of resources to ensure wide and timely availability of these products. So this was about choosing a microcontroller. So last time we had discussed about a few of microcontrollers, like 8051, like PIC 16, PIC 18, AVR microcontrollers. I have decided that in this class, in this course, we will be discussing AVR microcontrollers. AVR microcontrollers. First thing, AVR microcontroller is not a single microcontroller, it's a family of microcontrollers. There are hundreds of microcontrollers available in this family, and they are broadly classified into 5 categories. We have classic AVR microcontrollers, we have Mega, we have Xmega, and we have tiny and special purpose AVR microcontrollers. In this class, we'll be discussing about Mega family, and in the Mega family, we'll be discussing about Atmega 328. AVR microcontrollers were originally designed by 2 students of Norwegian Institute of Technology, and then their company was actually bought and then developed by Atmel in 1996. So presently Atmel, or now we call it Microchip, they develop these microcontrollers, they design and develop these microcontrollers and sell these microcontrollers. All of the microcontrollers in AVR family are 8-bit microcontrollers, except AVR 32, which is a 32-bit microcontroller. Now you know what I mean by 8-bit microcontroller or 32-bit microcontroller. The families it has, I told you, we have a Mega family, we have Xmega. These are the categories of AVR microcontrollers. AVR microcontroller is a big family, and it has 5 different it is classified in 5 different categories: Mega, Xmega, tiny, we have special purpose, and we have classic. And as I told you, we'll be discussing about Mega family, and in the Mega family we'll be discussing about Atmega, usually A and T is capital AT, Atmega 328. It's the name of a microcontroller. It's very common these days. And why I have chosen it? Because it's powerful, it's widely available, it is easy to study, it has its cost is very less, maybe 100 rupees per microcontroller. It has DIP package, quad flat package, both packages. Speed is good, we can use it in most of the applications. We'll be designing. And it has also got some trainer boards like Arduino Uno. They are built, in fact Arduino is built around Atmega 328. Arduino is itself not a microcontroller, it's a microcontroller board, a trainer board, and it's built around this Atmega 328. So there are many applications, and the resources available online are huge. So that's why I have chosen Atmega 328 microcontroller that we'll be discussing in this course. Previously at IUST we have been discussing, or we have been teaching 8051 microcontroller, but in the 8051 microcontroller it's not used now in applications. It has not an ADC, the speed is also less, the emulators, the compilers are not also available, and also it has not got a large peripheral set, like there is no ADC present in 8051. So I believe it's wiser to study Atmega 328. All AVR microcontrollers have something which we call that as RISC architecture, and Harvard architecture. It has RISC plus Harvard architecture. We'll be discussing about these terms RISC and Harvard maybe in subsequent lectures. So all standard features of microcontrollers, they are available in this AVR microcontroller also, like they have on-chip ROM, RAM, timers, IO ports, and they have these peripherals also like ADCs, PWM and other things, and they have also got some serial interfaces like I2C, USB support, and also many other things. So this is about the family. We'll be discussing very briefly what does these individual categories mean. What do we mean by Mega, Xmega, Tiny, Special Purpose and Classic microcontrollers. So let's start with Classic. As the name suggests, these were the classic AVR microcontrollers, the original AVR microcontroller, and usually they are 3 in number. We had AT90S2313. You don't have to remember these microcontrollers, these are just names, and you will always find these in books. AT90S2323 and AT90S4433. So these were the original microcontrollers. They were developed, original microcontrollers of the AVR family, and their computing they had very less computing facilities. Like these two had only 2 kilobytes of ROM and only 128 bytes of RAM. In fact, in these two there was no ADC. Number of input-output pins was very less. And then we have the next family, that's the one mostly used, that's Mega AVR, and the general name here will be Atmega and then some number, and these are more powerful than Classic. They may be having most of them have 120 instructions, that is, they support 120 instructions, and lots of peripheral capabilities like ADCs and PWM, and their program memory that varies from 4 kilobytes to 256 kilobytes. That means some of them have got 4 kilobytes, some more than, and some have got up to 256 kilobytes. Also, the number of the package, the ICs, they come from 28 pins to 100 pins. We have got an extensive peripheral set like ADCs, PWMs. We have also got tiny. You should remember that classic AVR microcontrollers are not manufactured or used nowadays. We have tiny AVR. The general name here is tiny, then some number. The examples of the Mega AVR are, there are many: Xmega 8, Xmega 16, Xmega 32, Xmega 328, Xmega 64, Xmega 1280. Now, tiny AVRs. These are those group of microcontrollers which have less instructions and smaller packages in comparison to Mega family, so that we can design systems with low costs and low power consumptions. Those systems where we need very less amount of computing facility, computing power. We use these tiny AVRs. They have only got 1 to 8 kilobytes of program memory and 8 to 28 pins in their package. Some examples are A tiny, 13, A tiny 25, A tiny 44. Then the fourth category is Xmega AVR. Again, the name here will be similar to the Mega ones. The only difference is they are more powerful than Mega ones, and naturally they have their cost is more than Mega. So these are used in some applications where we need large amounts of compute, where we have large amounts of computing to be done. Mega. And they have usually, some of them also have more than one ADCs. We may be having a DMA controller. We'll be discussing about what exactly this DMA controller is. Some of them even have some encryption techniques built in, like AES. These are encryption techniques using data encryption. AES and DS built in these microcontrollers. Some of the examples of Xmega AVR are at 80. Sorry, this was 80 Xmega. 80 Xmega 32 A4. 80 Xmega 256. And then the last category in AVR family is special ones. This is a group of ICs, group of microcontrollers that have special categories, and they are designed for some specific applications, like LCD controllers, like USB controllers, like FPGAs. For example, an example here will be AT90 USB 1287. So this microcontroller is designed only for to be used in the applications where we have to control a USB. So we have 5 categories. Classic ones, they are not designed and developed now. And we have Mega AVR. This is actually the largest group and most commonly used. We have tiny AVR. They are used in some of the applications where we need less amounts of computing, and less amount of RAM and ROM, and also their cost per unit is very less. We have Xmega AVR. They are on the other end of the spectrum. So they have large amounts of memory and large computing facilities, and also they have some special peripherals inbuilt, like encryption schemes, AES and DES. And then we have special AVRs. They are built for special purposes also, like we have 8090 USB 1287 built for USB controlling. The last thing we'll be discussing in this lecture is AVR product number scheme. AVR number scheme. How are these AVR microcontrollers usually named? As we may have seen, the first two digits here, the first two characters here are AT, and they stand for Atmel. And then the next ones, like S in case of Xmega or Tiny, it tells us about which family they belong. Do they belong to Tiny or Xmega or Mega families? And then the last number is important. How to decode this number? This number actually tells us the amount of ROM in microcontroller. And how to know that? Reading from left to right, like 1287, we have to find the biggest number that is actually the power of 2. For example, in case of this, when I read from left to right, the biggest number that is the power of 2 is 128. So this microcontroller will have 128 kilobytes of ROM. Similarly, maybe in this case, the biggest number reading from left to right, which is the power of 2, is 256. So at Xmega 256 has got 256 kilobytes of ROM. Similarly, this will be having 32 kilobytes of ROM. And ROM is important because it's where we store our program. Similarly, here the biggest number that's power of 2 is 8, so it has 8 kilobytes of ROM. Here we have 16, here we have 32. In this case, the biggest number that's power of 2 is not 328, but is 32 only. So the amount of ROM is 32 kilobytes only. In this case, 64. In this case, the biggest number is not 1280 because 1280 is not a power of 2, only 128. So this microcontroller has got 128 kilobytes of ROM. This rule has some exceptions, but in most of the cases it's very valid, that the last number, from this we can deduce the amount of ROM a particular microcontroller has got. So in next lecture, we'll be formally discussing Atmega 328. 80 Mega. It belongs to Mega family of AVR microcontrollers 328. And as I have already told you, the biggest number reading from left to right will tell us the amount of ROM. So this microcontroller has 32 kilobytes of ROM. In next class, we will be discussing about many more features of this Atmega 328, like let me just tell you about some of its features. It has 32 kilobytes of ROM. It has also 2 kilobytes of something which we call as data RAM, where we can store data. And also it has got 1 kilobytes of EEPROM. And also it has 23 IO pins. Eight number of ADCs. There are 3 timers. So this is the basic information about Xmega 328. 32 kilobytes of ROM, 2 kilobytes and 1 kilobytes of data RAM and EEPROM respectively, 23 IO pins, 8 number of ADCs and 3 timers. In next class we will be discussing about its programming model, the number of registers, and how we'll be introducing like we introduced in 8085 microprocessor, the assembly language instructions of Xmega 328. Thank you.